Hello and welcome to New York City Category Theory seminar in the Graduate Center today in person. Emilio Minichiello is going to talk about a mathematical model of package management systems. And take it away, take it away.
All right, so the four questions.
Born.
Where I was born, New York.
All right.
Where I did my undergrad, Queens College, CUNY. Where am I doing my PhD? CUNY Graduate Center, here. And where do I want to be in 5 years?
Oh, no, you don't have to answer that. Where are you going?
Okay. Yeah, so my talk today is going to be about mathematical model of package management systems. It's a paper on the archive by me, Emilio, and it's joint work with Gershom, Bazerman, and Raymond, Puzio. Here's my outline for the talk. I highly doubt we'll get through all of it, but we'll do our best. So let's start with the motivation. So package management systems are pervasive in modern software systems. My co-author Gershom is one of the people who is involved with a package management system for Haskell. So let me give some examples of package management systems.
NetSuite.
Is that
NetSuite?
That's, I don't know that one. But I'm thinking of like Homebrew for Mac. NPM for JavaScript. Pip for Python. And then package for Haskell, which is what Gershom works on. And if you've ever worked with any of these, you'll know that they could use a heavy dose of mathematics to help them out. So what we wanted to do was come up with a mathematical model.
Well, what do they do?
What do? They install packages in your computer. So say I want to run a program on my Mac, I could say brew install so-and-so. Right? And then what Homebrew will do, it'll check my system and see if everything that this package needs, that it depends on, has already been installed. Okay? And it'll give me an error if all the dependencies haven't been met for the program I'm trying to install. That's what all of them do.
Okay, but the top one is for a Mac. The other ones are for programming languages. So
Right.
So how does that work? I mean, you're running a certain programming language?
Yes. So say I'm running Python, and I want to use some kind of statistical library. Exactly. So you might, think of them as a library.
Okay.
Installation systems or something.
And then it'll load dependency libraries, like let's say like a logger to log things out. It might use that.
And then we have change the dependencies, which is where it gets tricky, and we need the math.
Okay.
Right.
And versions and blah, blah.
So packages can depend on other packages, but they can also depend on multiple versions of packages. So we have to take that into account. So here's an example in NPM of what something might look like. So here's a .json file that you might see for NPM. Try and do this kind of quickly because it's not super important for what follows, but just so you get a flavor of what these kind of things are. So the important part here is the dependencies. So it might depend on another package, maybe React. And maybe it also depends on Webpack. And on certain versions of these other packages. And perhaps it can accept an actual range of versions of a package. So here, this would denote several different possible versions of this package Redis that it could depend on. So when translating this syntax over, this could be written as, this is basically giving you a logical statement of things that this package leftpad depends on. So you could say it depends on React, and it depends on Webpack, and it depends on Redis 4.3.0, or it depends on Redis 4.4.0, or Redis 4.5.0. You get the idea. So we have logical statements and an OR here. So we need to include this in our model. Okay?
And by the way, I should mention that of that thing you show from JSON files, only the dependency part of it that we are modeling.
Exactly.
You don't need knots, for example. I mean, a system can't work if it has this, isn't it?
Sure. That's something that you could definitely ask for. In this particular model, we're not going to worry about those kind of things.
Just to get ahead, he says structures with choice. So that would be another possibility of choice with conflict. We're only considering with choice, not with conflict. Conflict would be not. We're just not considering not.
Okay, but these systems can deal with that.
Our particular mathematical model does not have that yet. So, gotta walk before you can run.
No, right.
These systems sort of deal with it all in different ways.
Yeah. So now we're going to start formalizing a mathematical model that we want to capture some of this behavior of dependencies. So a pre-dependency structure with choice consists of a finite set, E, and a function where this is the power set of the power set of E.
Okay.
So what does this mean? So to every element, E here, I want to think of E as like a set of packages. And I want this function to encode the dependency structure on those packages. So say I have E is the set A, B, and C, and then I have the dependencies of A consists of the set that contains the set BC. And I have maybe B depends on A as a singleton and C as a singleton. Okay? And then maybe
We're assuming that within the double brackets is an OR, and then within the single brackets is an AND?
so this we're going to translate to as B and C. And this we're going to translate to A or C.
Right,
So A depends on B and C, and B can depend on A or it can depend on C, and C doesn't depend on anything.
Which translates to false. No, it translates to verum, sorry.
Exactly.
every logical formula could be put into DNC.
No.
What does it go?
No, yeah, this is, yes, a form of that, yeah, a form of the thing with or on top of and or
Right,
and,
right.
but since they,
Okay.
distribute, you can do it either way.
Right.
So given this structure, so say if this is a pre-DSC, that's short for this here, so pre-DSC, we call if I have a set X in depth of E, I call X a dependency set of E.
I remember, disjunctive normal form.
Yes, that's right. Yeah,
Very good.
exactly. Yeah.
Or we'll call it a depth set for short.
Yes.
Okay? So, what is a pre-DSC? It's a finite set with this choice of a bunch of dependency sets for every element. Okay. Now, that alone by itself wouldn't be super interesting, and it wouldn't really model what we want in everyday life. So what we want to do is restrict to a smaller class of mathematical objects that more accurately represent package management systems in real life. So we say that a pre-DSC is irredundant if whenever X and Y are dependency sets of E, X is a subset of Y, then X equals Y. So this means that whenever I have an element E and I look at its dependency sets, they're minimal in some sense.
Don't you also want to make sure that E is not in X or Y?
Yeah.
Well, we're getting there, we're getting there.
You jump on the
Otherwise
gun.
you can have circles.
Yeah.
No, that's exactly, no, but we're
Okay.
getting to that condition.
Okay.
Yes, no, that's definitely something we want as well.
Yeah, this is a convenience, that's a must.
Yeah, that's
For sure. So this is trying to say that we want to get at minimal dependency sets. Because it's not very interesting if we want to look at any possible dependency sets. Because if A depends on a certain set and I add more things and I'm not modeling conflict in any way, then that's not super interesting. So this is a condition we're going to put. Okay, so that's the first one. Next definition, given pre-DSC, we say subset is complete if for all X in X there exists a dependency set. Maybe I'll say little e here, stay consistent. So I have a set D upper E. I'm going to use this notation throughout the talk. So this is a dependency set of E. So that means it belongs in this set. Okay? So I have a subset of packages. I say that subset is complete if for every package there exists a dependency set that belongs to X. Such that, okay? And the intuition here is that if I'm living inside of X, I can still load all of my packages. I don't have to depend on anything outside of X. There exists a dependency set for every element in there. So, let's look at an example. So here, what do we have? So if we look at the subset BC, this is a complete subset. Why? Because B has a dependency set C, and that's contained in this set, and C has an empty, depends on nothing. So that means that this is a complete subset of packages. Okay, good.
Cleverly erasing the the table of contents.
Exactly.
It's all on
Yeah,
videotape.
there's no proof that it ever existed. Okay, so now let's introduce the main definition. So we say that a pre-DSC is a dependency structure with choice, or DSC, if the following hold. So first we ask that it's irredundant. Then we ask that for all packages, def E is not empty. Now, here we see that dependency of C is not the empty set. It contains the empty set. But that's just to rule out some technical stuff. Here's the condition you wanted. So if E is a package, and D is a dependency set, then E is not contained in D of E. And
Well, what about a third level? What about another level?
We'll get there.
we'll get there.
Yeah.
So now for all packages and for all dependency sets, I want them to be complete. Okay? So these are the conditions I want to model real use package management systems.
So the completeness will imply the other one.
I know. Emilio, can you do an old man a favor? Can you go back to completeness over there and just say the sentence that you said before, explaining what it's about? Because now I see it's really central.
Given a pre-DSC, so
Right.
this is a finite set,
Right.
structure on it, right? I have a subset of packages. I say that subset is complete if for every package in that subset, there exists a dependency set contained within X. So suppose I choose a set of packages. For each of those, I can load them with everything contained, only with things contained in X.
Right, so if I hand you a disk with only those packages, I could still set the system up.
Okay, thank you.
So maybe I could load it with packages outside of X, but there's a possibility. It's possible.
Just
to load
using
it.
X.
Yeah.
Yeah.
So it's complete, so you don't need anything else. Okay,
So I
fine.
want the dependency sets to all be complete.
Right.
Okay? So now, given a DSC, we say that A can depend on B if there exists a dependency set of A such that B is empty of A. Say A must depend on B
Is this the unique?
if for all dependency sets. So then here's a little lemma. If this is a DSC, A can depend on B, and B must depend on C, then A can depend on C. So maybe I'll prove this really quickly so you can kind of get a feel for how all of these arguments are going to work. So A can depend on B, so that means there exists a dependency set such that B belongs to it. And for every dependency set, B must depend, yeah, for every dependency set of B, C must be contained in it. But now, so for all but this is a dependency set, so it has to be complete. So that means B has to have a dependency set contained in D of A. But every single dependency set of B contains C. So that means C is in DA. Okay? So therefore A can depend on C. Probably shouldn't have even written the proof down, but that's the idea. And that's how kind of all these arguments go. Okay? Any questions?
Quick question, just going back to the previous board. D2 basically just says that E can't depend on itself.
That's right.
Okay,
That's right.
double checking.
So you see, because the completeness, that's why I couldn't do it recursively.
Yes. So this implies that E cannot depend on E. It can't depend on itself. There can't even be a chain, like you're saying.
A chain of two.
Yeah, that doesn't work because of completeness. Okay. So I have a DSC, and I have two subsets. Say X reaches Y, if there exists finitely many subsets. Oh, sorry, I'm thinking of the wrong one. If, first of all, X is a subset of Y, and for all packages in Y, there exists a dependency set such that D of Y is in X. So that means that everything in Y can be run from packages in X. Okay? Say a subset is reachable, there exists finitely many subsets such that so the idea is that I can eventually build up all of my packages from nothing. Is that all right with everybody?
Can you phrase this by saying that if you take the transitive closure of imports, you get the whole thing? Is that?
Yeah, starting with the transitive closure and start with the empty thing.
Right.
Because obviously I think
Yeah.
transitive closure I get another relation, but here it's only the case of that relation where one of the things is the empty.
Okay.
Yeah, so you do the transitive relation, the transitive closure, and I see if it's connected to the empty set.
Okay.
Is there an algorithm to tell when something is complete?
Oh, what?
A theorem.
Yeah, check.
Yeah. It's not hard.
No, it's not hard. Everything's fine.
Nothing.
Got kind of a lame one.
Yeah, it's definitely decidable. Now, okay, so now proposition. Given a DSC, a subset is reachable if and only if it is complete. So this isn't obvious. The proof isn't super hard, it's a little tricky. It uses the finiteness assumption and the completeness. So this makes our life easy because checking completeness is easier. I mean, it looks easier than checking if a subset.
And it helps justify the definition.
Exactly. I will say it relies on the following lemma. It relies crucially.
Which way is easier, if and only if?
Just give me a sec.
No problem.
If it's complete, it's easy because all the points is already in.
Right. Yeah, so that's easy.
I suppose the quicker person complete, I've got a whole bunch of things I have to combine
Good,
together.
good.
Right. So so this relies crucially on the following lemma that's going to come up again later. So I want to say this now. So if you have a complete subset, there always exists an element in that complete subset such that I can remove it and it's still complete. So rather than prove this, I'll show you an example. A depends on B and C. B depends on just C. And C depends on nothing. Okay? Well, then if I look at ABC, this is a complete subset. And I can remove, what can I remove here? I can remove A, and it's still complete. And I can remove B, and it's still complete.
So basically proven by induction.
Mm-hmm. It's
Yeah.
like a Borean rings, where you can cut them and they're still connected.
Right. I'm going to leave this here.
Interesting.
So basically, if your computer works now, it worked before.
Yeah.
Exactly.
Yeah, right.
That's a great way to put it. All right, we got to part 3. That's pretty good. So,
And it's totally understandable.
so now, given a DSC, I want to analyze its structure more closely. So I'm going to do a construction. Let RDP of E denote the set of reachable, and because of that proposition, you can write slash complete. This stands for reachable dependency poset. Okay? So this is a set and it has an ordering on it by the subset relation.
So these are all the ones that you want.
These are all the ones I want. These are all the subsets of E I care about.
And do you want more higher up or lower down? Well,
I don't want,
What do you
I'm
mean?
impartial.
yeah, it's a post set, so
Yeah.
do you want bigger
Well, the
ones?
higher up means, right, that
It
I've
has
installed
more
all my
things in it.
packages, the lower down means I'm installing some of them.
Right, and so, and yet it's still reachable, so you want the smaller one.
We don't know which one we want. We want the smart post
We just
set.
wanna know what they all are.
Okay,
I mean, now we just wanna know what they all are at the moment.
okay.
So this represents the possible states that our package management system can be in and be a valid, set of packages that are loaded in the system. So let's do a nice example.
And you put it on all of them because if we wanna figure out the optimal thinking, well, which path in this is might be the best ones. Nice into the end result, but how do you get the optimal or something like that?
So A can depend on B, or it can depend on C, and then B and C depend on nothing. Okay? And now I'm going to describe its reachable dependency poset by drawing its Hasse diagram. So I'm not going to use parentheses for this. We'll just write elements next to each other. That's what I need here. So this is the Hasse diagram of this DSC. Okay? And you can check that this is a DSC. So all of these sets are complete. It's easy to check that. The only set that's not contained here is the set containing A. Because A needs B or C. So it can't just run by itself. Okay, so now we've made a construction. And we want to know more about its structure. So I'm not going to keep writing given a DSC. So if X and Y are complete, then their union is 2. And why is that? Well, I need to check that if I have something in the union, then it has a dependency set that belongs to it. Well, if I belong to X union Y, then I belong to X, or I belong to Y, or I belong to both. In either case, both of these are complete. So they have a dependency set in one or the other. So that means it belongs there. Okay? So what that implies is that if I have a DSC, then RDP is a finite join semi-lattice. And it has a bottom element given by the empty set, which is always complete. Okay, so I'll just put a word to this. Now, intersections of complete subsets are not always complete. But that doesn't mean that we can't put meets on this.
You just need to complete them.
Right.
But it makes sense. I mean, X means you have enough things you can do. Y means you have enough things you can do. That's what completeness is. So for sure, if you join them, for sure, but the intersection might not have enough.
That's right. But there is something else we can do.
But if you have X and Y, then you might get more possibilities.
So let this denote the set of packages in the intersection. These are both subsets of the DSC. I want to look at all the points in the intersection such that there exists a dependency set contained in the intersection. This defines a meet. This is a meet. So first of all, this is complete, almost by definition. And it is the meet of x and y and RDP. Okay? And it has a top element given by the whole set. So therefore, RDP of E is a finite lattice. So that's nice.
Does it have a bottom element?
It does have a bottom
Yeah.
element given by the empty set. The empty set is always complete. Okay, so I've given a construction which says for every DSC, I produce a lattice. But we're in a category theory seminar.
So we have to say if it's the distributive lattice.
Well,
We're
that,
getting there.
that's something I have to ask. But even before that, why don't I ask if this construction defines a functor, right? So, is this construction functorial? Well, I haven't given you a definition of morphism yet, so the question doesn't make any sense. So let's define morphism. Need to define morphisms of DSCs such that I get RDP is a functor from some category of DSCs to finite join semi lattices opposite. Okay, so I need to define a category for you guys.
And I guess we should just point out here that, yeah, we only, by that, we only want it to preserve the.
Yeah. What's the opposite? Well, you didn't tell us what the morphism is anyway, so.
Right, so I have to do that, so let me do that now. So, definition, given DSCs, a set function from the underlying sets is called a map or morphism of DSCs if, so first of all, if I have a set function between two sets, I get a function in the opposite direction between their power sets by pulling back subsets. Then what I can do is I can restrict this function to the complete subsets of E, but that might not land here. So I want to know when it does. So I'll say this set function is a morphism of DSCs if this map lands in RDP of E. Equivalently, F pulls complete subsets back to complete subsets. Okay? So that's what I mean by a morphism of DSCs. Now, it's pretty non-trivial to know when this is going to happen. And it took me a long time to understand what they were, but it turns out, you know what, this is a proposition, because it took me many months. So set function is a map of DSCs if for all E and E and all dependency sets of E, there exists all dependency sets of F of E, sorry. There exists a dependency set of E such that that condition holds. So you can check that condition relatively easily, and it'll tell you when a set function is a morphism of DSCs.
What happens if I would just take a natural transformation?
What does that mean?
In other words, you have a map from E to power set of E. You have another map from E prime to power set of E prime. You have a map from E to E prime, and you have power set.
It's too strict.
Yeah.
It's too strict. Yeah, that was kind of the first thing I wanted to check. We have a very strong check on what we want our morphisms to be. They have to be morphisms such that this is a functor.
Also,
This is precisely what you need.
I should mention one, intuition of this that Gershom and I were using is, it's kind of like in topological sets where I have, special sets there are these already open sets. And I want a map is continuous when opens.
In reverse.
Right.
And it turns out that those sets that appear in that condition are actually special. So,
Does it have any application, these morphisms of DSCs? Could you think of some?
well, yeah, I mean...
Well, that's why we have the next section.
Yeah, I erased it, but
Those is always one step ahead.
Yeah, he really is.
Okay, sorry.
So the subsets of the form here, where E is just an element and then I have a dependency set, these are special. The sets of this form are precisely the join irreducible elements of RD. Okay, so that means that I pull back join irreducible elements to join irreducible elements. And if you don't know what join irreducible means, it means that if I can write an element as a join of two other elements, then if this holds, then or that holds. And is not the bottom element. Okay. So that's what join irreducible means. Okay, so we have a nice characterization of that point. So you asked, when is this a distributive lattice? So let's think about that. Okay. When is this distributive? Well, let me tell you what distributive means. If L is a lattice, we say it is distributive if for all x, y, z in the lattice, did I do that right? Yeah, okay. So this is what it means to be distributive. It's a really nice example of a distributive lattice staring you right in the face. If S is a set, then the power set with the subset relation is a distributive lattice. There's all kinds of nice distributive lattices out there.
If you have bounds, if you have an upper and a bottom, don't you have that one implies the other?
Sorry?
One distribution applies the other? In a Boolean algebra it does, no?
Yeah. Well, in general, yeah, no, in the distributive, yes, a distributive lattice, you can define it using one or the other, if I remember right. In general, not just in the Boolean case. Yeah.
So there's a really wonderful theorem of Birkhoff.
A friend of McLean, we have to push in all category theory that we can get.
A friend of McLean, okay. He proved that a lattice L,
1990?
30, yeah.
1940?
1940,
Oh,
Yeah.
okay, so you McLean by then.
No, they wrote a book together.
is distributive if and only if it does not contain either
Oh, good.
the following
M5, K5.
lattices as a sublattice. So you have M3, which is more appropriately called the diamond lattice, and it looks like top A, B, C. That, and you can check this is not a distributive lattice. And there's also M5, which is called the pentagon lattice, which looks like so if I have a lattice and it doesn't contain these two as a sublattice, then it's distributive.
Is it a sublattice or a minor? No?
No, well, for graphs it's a minor, for lattice it's a sublattice.
All right. Okay. Right. Sorry. And then there's something called a modular lattice.
Yeah, well,
You gotta
the
stop.
second, the
You
first
gotta
one is
stop
modular, the
anticipating.
second one isn't.
Okay, sorry.
No, I'm good at this.
Sorry. No. Go.
That was, but that was my talk, previous talk in this seminar.
Yeah.
Okay, so proposition. If I have a DSC, RDP will not contain M3, but it might contain M5. So it's not always distributive. And in fact, it turns out that RDP is always a diamond free, which means it doesn't contain the diamond lattice as a sublattice. It's always diamond free and semi-modular.
And now we can bring McLean, because McLean wrote the nice paper on the characterization of semi-modular lattices, where in fact that lattice of dependencies we drew was the canonical one that shows up in that thing.
Now, I'm not going to explain what a semi-modular lattice is.
I have a question, just to go back to M3 being a lattice inside. The idea would be, let's say with the M3, that would basically say that a package can have multiple required dependencies that all depend on the same thing, underlying.
No, these are not packages in this picture now. These are package sets. So,
Package sets.
right,
These
so
are
the top
complete
element would
subsets.
be the set of, say, A, B, C, D.
Mm-hmm.
Right, so, so think about it. If the top element is the set A, B, C,
Mm-hmm.
the bottom element is the empty set.
Mm-hmm.
Then, what would happen is, if any two of, if you could have A, B, and C each like be individual dependencies.
Oh, I see.
Then you would also get the set AB.
Mm-hmm.
So this thing couldn't exist because you would be able to take more unions
A, B.
and add more sort of intermediate cells.
Okay.
Right, if you just start with A, you can't just jump all the way to have all three.
Right? If you ever had three things, right, you could always take their union. And the union of AB and the union of BC would have to be different unless either A, B, or C were actually, you know, this, one of them was actually, you know, the same as another.
Yeah. Right. Good question. So it turns out that RDP is always diamond-free and semi-modular. So this was first an observation, mainly by them, and the proof of it was kind of annoying. So I wanted to prove it another way, and it turns out there is another really nice way to prove it, and that involves antimatroids. So I Googled the term diamond-free semi-modular because I wanted to know more about it, and then a paper on antimatroids showed up. So let me, let's go to the beginning of the board. Are we all good on this? I can erase this. Maybe I should have put. It's fine. All right. So now. The second actor of our story is antimatroids. So, an antimatroid consists of a finite set E and a collection of subsets of E such that so I have a collection of subsets. They're typically called feasible sets, feasible subsets. So if I have A and B are feasible subsets, then their union is. If I have non-empty subset that's feasible, then there exists an X-mate such that so this might look familiar from what I wrote earlier. And E is the union of feasible subset, all of its feasible subsets. So this is what an antimatroid is. And there's some people who would quibble about including this part, but we're going to take this as the definition. Some people exclude this, but a lot of people include it. Sometimes they call them shelling structures. But anyway, so these are antimatroids, and it's really easy to define a reasonable notion of morphism for them.
Stop. Can you now say what a matroid is?
No.
And it looks something like a filter or something, no?
We leave it to the reader to reverse the appropriate arrows.
I don't see any arrows. That's
No.
fine. But fine, don't. I'll look it up.
Yeah, so the point is that matroids and antimatroids are both examples of what are called greedoids. And the point is that if you change some of the definitions or you include some of the definitions and not others, you get a matroid. And if you include different ones, then you get an antimatroid. And it turns out that they're not really as closely related as you would think, given the terminology.
Okay. And if matroids are mostly talked about as vectors in a vector space that are somewhat complete, what's the classical paragon example of an antimatroid?
So, I mean, I'm not a combinatorialist, but as far as I understand, like, you look at like subsets of trees.
In general, they relate to, they're a combinatorial version of convex spaces.
So, but I'll give you some simpler examples also. But they come up mainly in combinatorics and computer science.
You can get that intuition even if you think about adding a package. Where, right, if you're conflict free, like just like if you're in a convex space, you can sort of move further out on each dimension until you hit the end. Right, that's what you can do when you can keep adding packages until you run out of packages to hit. Each one is like a very small axis.
So we say a set function of antimatroids is a morphism if it pulls feasible subsets back to feasible subsets. So that's what a morphism is. So let antimat be the category.
Is this your definition, or is this a given, a known definition?
It's a good question.
Okay.
So this is the category of antimatroids. Yeah, I should say, you can find tons of literature that include the definition of an antimatroid. There's far, far fewer references in the literature that give you a notion of morphism of antimatroids. In fact, I never found one that said, this is a morphism of antimatroids. What I did was I found a paper that gave a definition of greedoid morphisms and then reduced it to the case for antimatroids, and it was exactly this.
Okay.
But it's also kind of the canonical, I don't know, it's a natural choice, I think, of a morphism of antimatroids, and we'll also justify it more in a moment.
Again, it's like open maps in topological spaces.
They're continuous maps.
Yeah.
Open maps means you take.
Oh, the
Well,
opposite.
I mean, continuous maps in terms of open sets.
Right.
Sorry, yeah, but open maps are different, right?
Okay, so, I promised you another example. Sorry, my notes are a little screwed up. So, all of the subsets of a set form an antimatroid. And let me give another example. If P is a finite poset, so if I have a finite poset, then P equipped with all of the downsets of the poset is an antimatroid. And a downset is a subset of a poset where if I have an element in that downset, then everything below it belongs to that subset. So this forms an antimatroid. Let me give a third example, but maybe I'll call it a proposition. C, then E equipped with all the complete subsets is an antimatroid. Furthermore, this extends to a functor. And I'll call it phi, so I'm not very creative. From DSCs to antimatroids. So this justifies both choices of definition of morphisms between DSCs and antimatroids. And now, the main theorem of the paper phi is 1/2 of an equivalence of categories. You can construct a functor backwards. It's a little tricky. You look at the feasible sets and you pick out some sort of minimal ones, and those form the dependency sets. So I'm not going to explain exactly how that process works, but it turns out that these are equivalent categories. Now, I've never seen a treatment of the category of antimatroids anywhere, but I've seen treatment of category of matroids, paper of Hunan.
Well, and you said at least with greedoids, you at least saw functors of some category theory.
Yeah, I saw a definition. I never saw an actual treatment of the category, but besides that, so now we have this interesting connection between the two that we had no idea that this would be true. We really didn't.
Antimatroids looks like a much larger category, and so one of these is the identity.
Well, it's an equivalence. So
No, I know, but if you compose it with its quasi-inverse,
it's an isomorphism.
It's not a larger category.
huh?
It's not a larger category. You might think it is, it's not.
Okay.
Okay, so from this, it's actually corollary by work of Sedley on antimatroids that the essential image of REP, the functor, is the category of diamond-free semi-modular lattices. So I got kind of a 2-for-1 deal. We got to know a nice connection with antimatroids, and we got to prove this result that we have been fiddling around with for a while. It was almost immediate.
Well, is it obvious why it's a corollary? I mean, you have
It's not obvious. It's not obvious. I haven't introduced enough to say why it's
Sedley has a theorem that codifies a bunch of folklore that was almost that theorem,
Yeah.
but not quite, that relates antimatroids and diamond-free semi-modular lattices. Diamond-free semi-modular lattices go back to the 40s as well, and they were studied by
von Neumann.
no, I'm trying to recall.
Another thing, Dilworth?
Yeah, they were Dilworth, and related to Dilworth's characterization theorem. So anyway, so that connection was established. So once we build the connection between DSCs and antimatroids, then we can just use the existing proof structures in the literature, which took some time to mature, but we don't have to reproduce them.
Right. Because before Gershom and I proved the theorem, so we're saying this, yeah, now it's...
All right.
So in other words, the next sucker who rediscovered the antimatroid,
Yeah.
because there are many times, several people since Dilworth who did that.
Okay.
Oh, I'm sorry, I have to add, one of the best paper on the history of antimatroids is from the mid-'80s, and it's titled A Use for a Frequently Rediscovered Concept. Okay, so this is really in that tradition of yet another rediscovery.
Who's the author of that?
I don't recall.
One minute here.
All right.
No, it's okay.
So now we have a nice category and an equivalence with something that appears all over mathematics. So why don't we take a look at this category and see what its structure is like. So the first thing one might notice about this category is it has the following adjoint pair. So if I have a finite set, I can make it a DSC by having no dependencies. And then if I have a DSC, I can forget and just get the underlying set. Turns out that U is faithful. And when you have a pair like this where U is faithful, we call that a concrete category. Okay? So this is really useful if I want to understand limits here. Because if this thing has finite limits, then use a right adjoint, so it has to preserve them. So it tells me that the underlying set has to also be a finite limit. So that gives me a guess, at least, of what finite limits must look like here. And similarly, colimits here, but they're only going to build colimits of these like free kind of DSCs. So it's not quite as useful. Anyway, so what are the initial objects? What is the initial object? Well, it's phi, the empty set, equipped with the unique map. Terminal object, we know what it has to be. It's a singleton set. Such that it doesn't depend on anything. Here's characterization of monomorphisms and epimorphisms. Let me write it like this. So I have a morphism of DSCs is a mono or an epi if and only if U of F is a mono or an epi. So it gives you a nice way to check. Let's leave that up there for a sec. Coproducts. Easy to describe. This is a coproduct where it's kind of the obvious thing. A little bit less obvious is the product. So the underlying set, as we said, has to be just a product. But what's the dependency structure? Well, I'll just say what it is, and not really explain why. But this gives you products and coproducts and the usual projection and injection maps are morphisms of DSCs. It also has equalizers. And these are a little bit fiddly, so maybe I won't describe it in any full detail, but be the underlying set of the equalizer, and then you have to be careful, because if you take the kind of obvious thing, it won't be a DSC. It won't satisfy irredundancy. So what you have to do is complete it with respect to irredundancy without ruining the other axioms, which is not super hard to do, but it's kind of annoying. But equalizers do exist. Well, when we have products, terminal object, and equalizers, that's good enough for finite limits. So DSC is finitely complete. However, but is not finitely co-complete. Does not have all colimits. So here's the example. Suppose I have the terminal DSC, and I have two maps, A and C. Now this DSC is one I drew before. This is the one where I had so this was where A depends on B or C. Okay? And this map sends the singleton to A, and this one sends singleton to C. These are both maps of DSCs, and suppose I have a coequalizer. So suppose E is a coequalizer. What do we know about E?
You're trying to mush things together, and it's not going to work.
Exactly. Well, if this is a coequalizer, I know F's an epi. But by this, that means that the underlying set function is surjective. So that means that the cardinality of E has to be less than or equal to 2, because this sends two of the elements to the same element. And this has cardinality 3. Now, there are exactly 3 DSCs with cardinality less than or equal to 2. Up to isomorphism. And they are given by, I'll just denote them like X and Y. They don't depend on each other. There is the terminal DSC, cardinality 1, and I have U depends on V. Those are the only possible DSCs with cardinality less than or equal to 2, and you check if each of these is a coequalizer, and it turns out none of them are. And you can prove that pretty easily. So, no equal coequalizer exists. So that tells you something interesting about this category and the category of antimatroids. Because every statement you prove about the category of DSCs, you're also proving about the category of antimatroids, because they're equivalent categories. All right, how much time do I have left? Doesn't matter? Okay.
My brain is full.
Your brain. All right, well, let me, we actually got to section 6, so I might as well just finish it up. It'll be quick. So as you said, RDP, when is it distributive? It turns out not often. You can characterize exactly when it's going to be distributive. It turns out that if you have a DSC E, RDP of it will be a distributive lattice exactly when every element has a unique dependency set. So I can't depend on this or this, I can only depend on one set of packages. When you have that scenario, then RDP will be a distributive lattice. But suppose I want to complete RDP into a distributive lattice. So it turns out the Bruns-Lakser completion.
Another frequently rediscovered thing.
is a completion of a lattice and it can be described in the following nice categorical way. So if you have a lattice, it has a canonical growth and decrease topology. I call it J dis for distributive. And you can think of them as all of the family of subsets such that when I take, such that they're distributive and such that when I take the join it gives me the element that it's covering. Okay, so you can give this a pre-topology and then you can define what are called thin sheaves. So instead of having a pre-sheaf which is a functor to set, I could have a thin pre-sheaf, which is a functor to 2, a category with 2 objects and 1 morphism, one non-identity morphism. And then you can define what a thin sheaf is. And then it turns out that the Bruns-Lakser completion of a lattice is equivalent to the category of these thin sheaves on the lattice. Now this is not, this is pretty well known, but we were able to get a nice characterization of it.
But it's not a topos, it's what is it?
Locale. It's a locale. It's like decategorified topos.
Well, instead of set to the category, you have the 2-element thing to the category.
Now, if L is a finite lattice, it turns out that the Bruns-Lakser completion is actually isomorphic to the downsets of the joint irreducible elements of L. So this gives the Bruns-Lakser a really nice characterization and a way of computing it. And if you take RDP of a lattice, I mean, if you take RDP of a DSC, that might not be distributive, but I can take the Bruns-Lakser completion of it, it'll be a distributive lattice, and then there's a construction I can do, which I won't delve into too much right now, but this will give me back a DSC. And it'll give me back a DSC that has unique dependency sets. So what this composite operation does is if I give you a DSC, it'll give me back a DSC, and all of the events will kind of be split up. So say I have A can depend on B or C. This will get split up into A depends on B, and A prime depends on C. It'll split them up into different elements. And what this structure describes is something called a Merkle tree in computer science. Wow. And I think I'll end there.
Thank you. Wow.
Any questions?
I have some comments.
Okay.
And maybe you can say if you've thought about them before. But first, one question. One of the things that you know they like to do is like where instead of importing an entire package, you import only the functions that you need in the package, right? And I'm wondering how your work that you're doing here relates to that. Would that be like basically trying to find a function such that you can create another DSC that has no dependencies by just sucking in the individual elements?
Our analysis here just happens to take the package level sort of as a concept. But you could look inside what we would call a package, and you'll find that some functions depend on other functions within that package.
Yeah.
And like the compiler will often actually have to perform that topological sort to figure out what order to compile and type check the functions in.
Yeah, because I mean,
So-
if you can split it up, then you can kind of maybe use the same algorithm to.
Well, right, the
figure out-
analysis decomposes, it works at any level of dependency.
Okay,
It's motivated by packages as a concept, but
yeah,
anytime you have a dependency system, including the topological system of dependencies within a package or outside of computer science entirely, these mathematical sort of structures
Well,
exist.
point being, instead of our set E being the set package, it could be instead of all subroutines within your packages,
Yeah.
and same story.
that's pretty cool. And the other thought I had about this as an application possibly is, there are version control systems that have the idea of patches, right? You know, like for example, Darks or Puzio have this theory of patches, right? I'm wondering how this would relate to that. So
Yes.
now we're talking about in source code level, whether we can say, okay, when do certain patches depend on others? It seems like a very similar question. Have you guys thought of
Yeah, so-
how that would work?
Yeah, so there is a paper
Patch
about category theory applied to patches, like you're saying. Unfortunately, I haven't been able to delve too much into it, and I don't know.
I would love to see some
Well,
follow-up.
one comment we should make with this dependency with choice, there's also, from, like I said, from theory of concurrent systems, Winston came out, you know, his notion of dependency, we think of concurrent systems, there was dependency with choice, without choice, so they might all.
For a lot of that stuff, you would need to put back conflict. The reason we don't have it is
Ah,
not because
yeah,
we think it's
that's right.
unimportant, it's because it's
It's a
very
difficult
difficult.
problem. I didn't think
and a lot
about
of
that.
work
Yeah,
has foundered
and
on
that's
it,
everything
so-
with
Right.
with
Well,
So we want to put it
Yeah,
back.
That's the hard
here.
part, otherwise you don't
Um,
need.
Right, part of the original strategy Gershom had was people oftentimes say, well, okay, doing conflict and choice both is hard, so
Yeah.
usually people say, we won't have choice with conflict, and the idea here was, well, let's see if it's maybe, what can we do if we didn't have conflict, but we had choice.
Yeah, okay.
On version control stuff as well, I would point out that, in a sense, when we have the multiple tree result, that is the canonical data structure for Git. So, we don't have patch theory a la Darks, but this does give you patch theory
Yeah.
a la Git, actually.
Yeah.
Because the branching structure is all very strongly determined and not reorderable
Yeah.
when you have a Git setup. So this actually does characterize Git.
Yeah.
I just want to say, this shows up also in LaTeX.
Yes,
Oh, yeah.
yes.
It's really a pain in the neck. sometimes.
LaTeX is an example I'd like to use when I present to
Yes.
mathematicians, because
Oh, I should have used that.
that's really where we're most comfortable with realizing that
Yeah.
I imported one package to, give me the O that looks right. And then I imported another package to
And
get the
everything
right
gets messed
bibliographic
up.
formatting, and then they can't coexist.
Right. Hey, Emilio, thank you. This was a great talk. Anybody else? Thank you. Thanks. It's a pleasure.
Awesome.
Okay. One second.